And then we're going to very quickly go through the last two types of modes of inhibition that we'll look at. So this is called uncompetitive inhibition. And this is where the inhibitor specifically binds only to the enzyme substrate complex. So it can't bind to the enzyme by itself. The substrate first has to bind. There's some sort of conformational change in the enzyme that allows for this inhibitor to bind, and then it binds to specifically this enzyme substrate complex, and in that way takes it out of the catalytic pathways to form product. For this type of inhibition, this affects both the Km and the Vmax. And what you might expect is if this is no inhibitor, or zero inhibitor. Let's try this again. Sorry. 0 micromolar inhibitor. And as the inhibitor concentration increases, you'll see lines that are parallel to each other. So let's say this is 10 micromolar inhibitor. And 100 micromolar inhibitor. Implying 1, remember that the y-intercept is 1 over Vmax, so that means that the Vmax is changing as the inhibitor concentration increases from this value, and it's increasing upwards. But the slope is remaining the same, so that means that the slope, the Km is moving, is changing in conjunction with Vmax. So that keeps the slope constant for all of these, which causes this parallel arrangement of the three lines as inhibitor concentration increases. So in this one, both Km and Vmax are affected. Unaffected. Okay. Now the last one is mixed. Inhibition. And in this one, this is a combination where the inhibitor can either bind to the free enzyme, or it can bind to the enzyme substrate complex. Okay? And so, and again, in that way, since it can bind to either of these, it doesn't require some conformational change caused by the substrate binding. All it needs is that the inhibitor is able to bind somewhere along the enzyme, and that actually suggests that the inhibitor might bind to some allosteric site instead of at the active site. So this is mixed inhibition, and in this case, what we see, if we look at our Lineweaver-Burk plots, this is 1 over S naught, 1 over V naught, same over here. Running out of space here. And so if this is 0 micromolar inhibitor, what we might see something like this. where we get convergence to a point that's not on the y-axis. And so it's not parallel, but it's also not converging at the y-axis, as would be expected for an uncompetitive or a competitive inhibition, respectively. So in this case, we would have both a difference in the change of the slope and at these different y-axes. So this is affecting somewhat both the Vmax and Km, but typically for what we call a pure mixed inhibition, or rather, we can also see, let me back up. What we can also see is that the Vmax is the only thing that changes, while the Km doesn't change. So Vmax changes, and that's apparent from the difference on where each of these lines cross the y-intercept. And Km can either stay the same or change. And so, in that way, by plotting these Lineweaver-Burk plots, so by increasing the substrate concentration and getting rates for product formation or for substrate consumption, in other case, we can get these rates, and we can plot 1 over V naught versus 1 over S naught, and by looking at the patterns as we increase the inhibitor concentration, we can determine whether an inhibitor is a competitive inhibitor, an uncompetitive inhibitor, or goes through a mixed inhibition mode.